Hi, thank you very much. This is a very good turnout. Probably not enough seat. I hope there's enough boxes. We ordered extra already, 20%. Maybe we should use a different room. Thank you for attending this promotion talk for Dr. Ying Zheng. And I think as we know, this 21st century, all the data is really in a digital format. And a lot of techniques we have been using to study them, to analyze, in the past has not been very effective in this new era of big data, artificial intelligence, all kind of thing, especially in the area of life science area. And so there's a trend toward convergence of different techniques in the past. And people don't work on silo a particular technique anymore, not just gene sequencing or not just proteomic or not just clinical data. You can see the trend is people start converging different disciplines, different data sets together to answer a bigger question. In due process, maybe some new discipline will come out. We don't know yet, but this is the trend. So convergence is the key. Convergence different technology to address a lot of multimodality, multi-scale data, and to answer translation aspect, how apply to disease. In this case, Zheng will talk about is a cancer and neurodegeneration. I believe he will give one example each to show you the favor. This is really a starting new convergent paradigm, very different from the past people get used to. And after all, it's all human body. Data is data. We measure human body different scale. It's the same disease. You have to understand of different scale and merge it together to answer bigger questions. Okay, so without overdue, let Zheng get started.
Thank you, Dr. Wang. Respected guests, dear colleagues, ladies and gentlemen, it's my honor to share with you our efforts to converging image with multiple omics data for biomedical research. Such convergence allows us to achieve better understanding on biological processes and obtain better therapeutic option for disease like multiple type of cancer and neurodegeneration disease like Alzheimer's disease and Parkinson's disease. For my collaborators, my team, and myself, these are what we believe in. These are where our efforts are, and these are where we have achieved some initial results. And hopefully you can find excitement and synergy with your work, and together.
I have to put on a mic on you. Okay. Good. Continue talking. Mm-hmm. Try now.
Test.
Okay.
Test. These are what we believe in, and hopefully you can find excitement and synergy with your work, and together we can move the biomedical research forward. So here we go. Organisms can be viewed, modeled, or intervened through multiple scales. Usually, these multiple scales were arranged in this stair-like fashion. But actually, the causality chain between different scales can build across multiple scales, even before the height scale of a population and the environmental factor and the lowest scale in the DNA. Like shown in this wonderful summary about cancer genome landscape. This picture shows the average median number of mutations carried by different type of cancer samples. So you can see that usually pediatric cancer and liquid tumor carry the fewest number of mutations. And the most solid tumor carried a median number of 22 to 66 mutations. And you can see there's an outlier group, consists of two types of lung cancer and melanoma. This type of cancers carries significantly higher, usually hundreds of mutations, somatic mutations per sample. And all these three types of cancer actually have a clear environmental or behavioral risk factors. Actually, within the lung cancer patient populations, the mutations carried by smokers can be as high as 10 times higher than the mutations carried by the non-smoker lung cancer patients. So that's an example of the causality chain between the population environment level and the DNA level. What we want to do is we want to use imaging as a quantitative phenotype layer of multiple omics models. Imaging and omics have various different properties. Sometimes imaging can have a better spatial and temporal flexibility, while the omics data is more in-depth and you have profiling in the individual gene or protein level, and it can be used for basis of hypothesis generation. What we want to do is we want to converge these two types of data together and to use the advantage of both. To use the image data as a layer, additional layer of multiple omics means that we want to build advanced feature for the imaging feature set. We want to discover the regulatory mechanism between the multiple omics, the DNA, gene expression, and the protein, how they work together to regulate the cell shape change. And ultimately, we think that if the image features can be considered as an additional layer of multiple omics model, that means image features can be used as drug targets also. And if we can do that, we can use such data convergence to achieve better and faster drug repositioning. That's our goal. So the first project focused on high content screening. Originally, the data was generated in 2006 to 2008. It was high content screening data generated by the group of Dr. Norbert Perelman, Dr. Chris Bartle in Harvard Medical School. It used Drosophila KC167 cell line. It's in the normal status, it's the round, mostly round cells. And it's used the reagent called dsRNA to target up to 300 kinases and phosphotases. So the biological process it targets on is protein phosphorylation. It want to find that which are kinases or phosphotases when knocked down will significantly change the shape of Drosophila cells. And they have a very detailed design of arrayed screening. And ultimately, I have more than 3 million cells to deal with. This is my first project when I come to America. And I was told that every cell counts and every gene matters. Imagine being told something like that.
Why did you use Drosophila cells?
Uh-huh.
Why did you use Drosophila cells? Why did you use memory cells?
Yeah, that's the expertise of Dr. Perelman's group. So they started this project as a general hypothesis generation process, and yes. So after we process all the data, we try to publish the data. We meet the challenge that we need to find a translational angle.
That's not my question. My question is, what is the logic of using
I think the logic is
Okay, we'll talk later.
yeah, okay. I think it's because the Perriman lab has established the system of RNAs, dsRNAs. So for each gene, they can be knocked down using multiple dsRNA, and all those dsRNAs in-house. So it's very convenient for them to finish such a screening. And then they generate all those data. They doesn't even need to go out of the building. And they generate all the data, and the computational guy just come in and try to make sense of it. And this type of screening doesn't really have a positive control. It's a hypothesis generation process. Usually, the screening will have a negative control and positive control. And we don't know exactly what how the shape will change after different kinase and phosphatase are knocked down. So this is an open question, and this is an open platform to try out all the computational technologies. So we get to work. First, we found that this Drosophila cell population are actually dominated by 5 phenotypes. The normal, the round normal ones, the elongated ones, the spread, the smooth edges ones, and the ruffle ones come up through the domain knowledge. The biologists immediately identified those, and we developed a computational methods based on these 4 phenotypes. We identified the 5th one. We named it the teardrop. Meaning that it's not completely elongated. One side may be round, and the other side may be generating a tip. So based on these 5 discrete phenotypes, which dominate about 95% of the normal cell population, and we generated a so-called quantitative morphology signature to describe the morphology of each individual cell based on the similarity to these 5 existing phenotypes. And based on this QMS system, we defined the functionally significant phenoclusters, meaning that kinase or phosphatase, when knocked down, that generating similar phenotype, we cluster them together. And we look at each cluster in detail, and we find that we can find biological meaning of each phenocluster defined this way. That means the functionality and of kinase phosphatase is indeed related to the shape that how the kinase phosphatase regulate the cell shape change. And we find that some of the kinase of phosphatase will actually generate intermediate phenotypes and increase the complexity of the cell population. Like when we put the normal cell population into a 2D distribution form, it will mostly look like this: normal cells and all 4 others. Some of the RNAi will generate a cell population right in the middle. Right in the middle, it blurs the boundary of different cell phenotypes, and created some normal phenotypes. And but that's only a small portion of the genes that can do this. Most of the genes actually, even after knockdown, the cell will do switch-like transitions sometimes with reduced complexities. It means that in the normal status, the cell will freely transit between 5 phenotypes. And you knock down some of the genes, the cells will be trapped in some of the valley of the phenotype. It's just like falling into a cult. Sometimes you forget the meaning of all other possibilities of life, and you focus on a couple of things to do. So maybe this is related to the disease process and and how cancer cell obtain the survival advantage. So we dig deeper. We found a highly conserved site of cell shape regulators that when we knock down this group of kinase phosphatases individually, and the cells will be trapped in two phenotypes, normal, a rounded one, or elongated ones. They forgot the other three possibilities, and the cells will shift between these two cell types. As a result, this leads to enriched ratio of elongated cell within the population. After knocking them down, the cell population is enriched with the elongated cells. So the center of this group of gene is P10, a phosphatase, and P10 is actually mutated in 10% of melanoma patients. And we can see the effect of knocking down P10, and it causes the cell to be trapped in two situations. And you can also see that the tumor section in the mouse. In this experiment, they injected the mouse melanoma cell line into live mouse and take an H&E picture, and to see that this is a P10 wild type cell line. This is a P10 deficient cell line. And they tried 3 different shRNA, try to knock down P10 in the mouse cell line, and they proved that 2 of them actually works. So they knock down P10 in this wild type cell line and inject the cell populations into mouse, and the cell section H&E picture also enriched with elongated cells. This is what we discovered. And so, as summarized by this news release for our paper in Nature Cell Biology, genes control cell shape behave more like light switches than tea kettles coming to slow boil. When I sent this sentence to my collaborator, he immediately said, "Who wrote this? This is perfect." The author of this sentence is Mr. David Breaker, the excellent scientific writer handling of news release. He passed away in 2015. It's only after that we got to know his story, his enthusiasm, and I actually feel honored to have him told our story. So Houston Methodist established the David Breaker Award and lecture in his honor every autumn, every winter. So I encourage everybody to attend, to get to know the world of scientific writing. So I think this opens the door to model the morphology landscape. In the previous slides, we mentioned a conserved set of gene regulators. That this group of genes, when knocked down, will trap the cell population into elongated status. So we further prove that not only the gene function is conserved between fly, mouse, and human, there are also conserved phenotypes across all the cell types. You can see there's a human breast cancer cell line, and there are different Drosophila cell lines. They all share certain cell type, and they all have their own also. And based on this, we build a computational model to illustrate the morphological landscape of the shape space that can be explored by the cell population under different treatment. So you can see the X and the Y is the 2 principal components of the quantitative morphology signature of describing the cell shape. And the Z-axis is actually the the ratio of normal cells. And each node here represent RNAi treatment. You can see the normal cell populations crowded mostly here, and most of kinase and phosphatase in our screening, when knocked down, it doesn't change the cell population too much. But some of them will completely generate normal phenotype, and a lot of them falls in between. So this model can not only we also proved that cell morphology can be impacted by the features like cell adhesion. Remember in the first slide that the number of mutated DNA can be impacted by smoking or ultraviolet light. Well, cell doesn't smoke, but cell can be impacted by the environment, by the way you culture them. And so when there are no adhesion, cell explore the shape space in a certain way. When there are a medium level of adhesion, it explore the shape space in this way, maybe illustrated by EMT. And when the cells are cultured completely crowded, and there are no flexibility available, and the cell doesn't change the shape too much. And this impact can be showed in this model too. It's all great. We published 4 papers for one project. It gave me the PhD degree and everything. But I always feel that there's an unfinished business. If only we had matched the imaging and the multiple omics profiles for those RNAi treatments. You see, the treatment RNAi works in this level, the RNA level. RNAi injected in cells, it dissolves the RNA so that the protein doesn't translate. So the protein lost function. And the target process is actually in the protein level, protein phosphorylation. When the kinase of phosphatase doesn't translate, and the protein, the target protein doesn't phosphorylate properly. But the readout is in the cell and cell population level. We are missing the link for the detailed pathway that underlying the shape changes. In a word, we talk about phenocluster, but look how large some of the phenocluster is. We have 300 different genes total. Some of the phenocluster contains 80 or 60 different genes. So it means that some of the double-strand RNAs in the same phenocluster, they induce similar phenotypes. But does it mean that they are working the same mechanism? So in the last subplot of the Nature Cell Biology paper, we did we try to stratify a phenocluster. The phenocluster leading by P10. The phenocluster that when knocked down, that traps the cell population in normal and elongated status. You can see we have more than 10 genes we got from the screening, Drosophila screening. They all do the same thing. So the yellow ones means the function of such gene are validated in mouse model, mouse melanoma cell. The green ones means that not only validated by mouse melanoma cell, the function also conserved in human melanoma cell. So they are very well conserved functions. So now we want to stratify this phenocluster. Do they work in different mechanisms actually? So it's a very, looking back, it's a very naive method. Our biologists listed a group of pro-elongation genes and also a group of pro-rounding genes. And the computational guy chip in and look into the protein-protein interaction network and calculate the distance, average distance between each screening hits to each of these genes is established a function. And we try to compare that we do a student's test to compare whether the gene is significantly closer to one group than the other. If this gene is significantly closer, for example, they are directly connected to the gene to the proteins in group 1, but it will take them 4 to 5 different steps to reach genes in group 2. We say that maybe they are functionally closer to group 1, and they may be the negative inhibitors of the pro-elongation genes. So on the opposite, they may be the positive regulator of pro-rounding genes. So in this way, and the length of the edge here is proportional to the p-values, minus log 10 of the p-values. The longer edge actually indicates more significant distance of significant differences between the distance to this group and another group. And you can see more than half of the screening hits can be actually attached to one of the groups. With the other 6, they don't show significant difference. But if we want to look at them in detail, we can do that. So next, we don't want to stop here. So we work to converge image, proteomics, and genetic data across 11 mouse melanoma cell lines. So here, we don't knock down genes. We don't apply treatments. We show the variance through the genetic background of 11 different mouse melanoma cell lines. And this 11 cell line, 3 of them carry the BRAF kinase activated mutation. So this mutation actually appears in 60% of the melanoma patients. And 6 of them have NRAS activated, and 2 have NRAS activated and BRAF dead. So we follow a very straightforward regulation hierarchy. You can see the GTPase is actually upstream kinase of phosphatase. You can imagine that when you knock down a GTPase, maybe a lot of kinase phosphatase will be impacted. So based on this, we do the mass spectrum to get the abundance data of 4,800 proteins, and we got the intensity of more than 16,000 phosphorylation events of those proteins, and we measured 166 imaging features for each cell group, and all these are measured across 11 cell lines. Without any treatment, we want to see that what's the difference caused by genetic backgrounds. So it's a rich data set. Again, every causality pair counts, but there are tens of millions of them. How do we determine that? Where do we start? We start from the genetic level. So we carried out ANOVA and multiple comparison tests, and my collaborator said there are 3 possible comparisons: B versus N, B versus NB, and N versus NB. They say the third genetic background, NB, is very different from the other 2. If you can find the significant difference between the BRAF and NRAS, that will be perfect. So we did the ANOVA, and we found that only 8 proteins out of 4,800 showed significant changes of abundance across all 3 comparisons. And one of them is P62, or SQSTM1. And then how about phosphorylation? Among more than 16,000 phosphorylation, only 8 showed significant changes across all 3 comparisons. And 3 of these phosphorylation events belong to SQSTM1. Okay, you search SQSTM1 melanoma. There are paper coming up right now, 2019. People, this is a hot area. Let's start here. Mass spectrum data actually identified 16 significant events belonging to this protein in this data set. Three of them show significance, like we said. So we come to identify the correlations between significant correlations between shape and phosphorylation. Remember, all those are measured across 11 cell lines. So we compare the correlations between shape feature and phosphorylation intensities across 11 cell lines. We calculated the Pearson correlation coefficients, and in this figure, we show the 13 SQSTM1 related phosphorylation events actually have significant correlations, p-value smaller than 0.01, with 25 different shape features, 25 out of 166. And if I labeled the three genetically significant events in yellow. And the red edge means positive correlation. And the blue edge means negative correlation. The thickness of each edge is proportional to the Pearson correlation coefficients. The thicker ones means better correlations. This is a network between shape feature and phosphorylation events. And how about phosphorylation and kinase phosphatase? Which kinase and phosphatase are actually regulating SQSTM1 phosphorylation events? We go through all the kinase and phosphatase from the protein abundance data. We found that there are 12 kinases, and there are 12 kinases and 4 phosphatases with significant correlation to at least 8 of 16 SQSTM1 phosphorylation events. It actually shows the pattern here. Those are phosphorylation events. Those are the kinase and phosphatase. Again, red means positive correlation, and blue means negative correlation. Let's converge. So we have a 3-layer network between kinase and phosphatase and the phosphorylation events. Phosphorylation events exclusively from SQSTM1 and some shape features. For the shape features, we focus on first 20-something because the later more than 100 image features come from very complicated mathematical transformations. It may be difficult to interpret. The first 20-something is just the length, the roundness, and the area, things like that. So let's focus on this. Between the p-value of 0.05, absolute PCC larger than 0.64, and the very stringent p-value than 0.01, they are very different. You can see they are very different. For one thing, in this figure, there's only 3 shape features left, and only 1 phosphorylation events have a significant have a correlation with shape features that significant. All others are gone when we raise the bar for the significance. And there are remaining questions. We call it Matthew effect. Matthew effect is actually from Bible, and people want to explain it as the poor become poorer, the rich become richer. And in the graph theory, it is expressed as a Barbarossi theory. That certain network, the node that with higher degree is easier to take up more new nodes when the network expands. So in our case, we want to see that when we change the cutoff for the for cutoff of correlations for this figure, to try to include more shape features into it, do we see any massive effect for these phosphorylation events? Yes, we do. For this, when we reduce the cutoff for the phosphorylation and the shape feature correlation from 0.8 to 0.7, 7 new shape features are introduced. 6 of them are connected to this one. And this is exactly the same one that's from the previous figure. And but there are also reverse massive effect. This node in the original figure only have one connection. But when we expand the network, it also take up 6 of the 7 new shape features. So this is something worth looking at. And also, all the order 0 shape features are missing. Order 0 means this shape feature doesn't have a unit, roundness, or ratio between two measures. This type of shape feature doesn't have a unit, right? And we saw that between all the phosphorylation events and all the shape features, for the SQ-STM1 phosphorylation events, the shape features with significant correlations are all order 1 features, like length for the cell, length for the nuclei, or order 2 features, like the area. None of the order 0 features shows any significant correlations to this phosphorylation event. So this is another thing worth looking at. And a third one is positively correlated phosphotasis. Usually phosphotasis is downregulated of the phosphorylation process. But here, there are phosphotasis positively correlated to these events. So our collaborator is excited. Maybe it means something. They have a theory about this phosphorylation regulating the length of a certain mitosis stage. So at the end of the day, I want to build a 3D graphic visualization like this. Nobody ever did that, amazingly, but I think it's worth doing. It will show very clearly the structure of the converged network. We start from the focus phosphorylation and connect to the KP kinase phosphatase abundance and also the shape features. And the next is a morphological phenotype as prognostic markers. Our collaborator published a paper, identify 5, do the same thing, but in the 18 breast cancer cell lines. They take the shape feature, they take the gene expression, they identify 504 shape-correlated genes and transcripts for 20 shape features. So they publish the results, we take the raw data, we map them to the Broad Institute, the CLUE database. And we want to see that whether we can find a drug family that can regulate this shape-correlating gene groups. And this is, we find the 14 shape features are connected to 410 individual compounds. Oh, it's too hard to see. So how about we look at the annotation of the drug function and simplify the data. It's 14 shape features connect to 37 compound families, this feature. And then we say, how about we just we only look at the edges that involve more than two compounds. In this figure, we have 13 individual drug shape features, and we have a group of drug families each drug family are connected to a shape feature. If this is a black edge, it means it's a negative correlation, negative regulation of this group of shape feature. Red means positive regulation. And this dialogue actually happens. I told Dr. Wang, this looks like Australia. Dr. Wang said, then where's Tasmania? I say, right here. This one doesn't have any drug family making the cutoff. It doesn't mean that it doesn't connect it to any drug in the previous version. But when we apply stringent cutoff, that every edge must represent more than 2 compounds, it was left out. So this is some interesting hypothesis we can pursue. And then this is actually from the same data set, where we measured both the gene expression and shape feature across 18 breast cancer cell lines. We find that some of the drug treatment can completely reverse the order of certain shape feature. Like this is a nuclear eccentricity, whether the nuclei is round. So the cell lines, 7 cell lines, is ranked this way, from 1 to 7, these 7 cell lines. Without any treatment, it ranked this way. And when we apply this treatment called Y27, this is a ROC1 rho-associated protein kinase inhibitor. When we apply this group of treatment, with or without TNF-alpha added into it, the order of the same shape feature completely reversed. The smaller, the cell line with the smallest number of this shape feature become the cell line with the largest one after the drug treatment. And the same thing for colony area. Colony area, when you culture the cell, whether it will generate a cell population around them. So it looks more significant that notice that here we have 8 cell line. The order is different from this, and it add a new one because in this one, in this shape feature, this is actually an outlier. Before or after treatment, the value of this shape feature for this cell line doesn't change, but it changes here. So it changes because of this cell line. Originally, this is the smallest, have a smallest colony area. After the same treatment, this cell line have the largest one, and all others doesn't have any colony. So these are all drugs treating cell lines, but we are looking for translational angle. We think that we can use it to control the subgroup within the EMT cells in vivo. This is a paper published by our group in 2016. They use a cell tracking system that after EMT, before EMT, the cells are red. After EMT, cells become green. And they found that the green cells can be divided into 3 subgroups. Fibroblast-like, that's tightly attached to the ECM, and the silent ones, and the migratory ones. So I think one of the translational angle of what we do is to take the image feature, shape feature of these cell populations and try to apply drug, control the EMT cell group in the silent subpopulation, to make the EMT cell population enriched with a silent subgroup instead of doing the migration. And we did some exploration using the intravitreal imaging. So basically, mathematician can do anything. Hands up if you know this trick. You search this question in Google, the answer will be given by calculator. It's 42. So this is attributed to the Douglas Adams, the Hitchhiker's Guide to the Galaxy, the series. The gist of this story is that only when you know the questions will you know what the answer means. It is extremely true when you are doing the modeling using doing the screening using cell models or animal models. So we move forward. We want to apply the same strategy to the Alzheimer's disease, neuron degeneration. We hypothesize that the modeling of large pharmacological data with large drug screening data may identify new drug hits for AD. And we want to expand the width and the depth of AD drug repositioning. We want to try more drug more effectively. We want to try more drug purposely after we know the disease mechanism better. So far, we have obtained. We are collaborating with the MGH, and we use a 3D cell culture, and that can spontaneously accumulate phosphorylated tau, and in the cell, and we apply a high content screening to select the drugs that can eliminate the p-tau accumulation. So far, we obtained 35 primary hits from the high content screening of more than 2,600 drugs. And we use the 38 hits as a base to do the prediction. And we take the compounds with a certain phenotype and combined with the public available transcriptome data. We hypothesize that if the compound shows similar transcriptome change, maybe they can generate a similar phenotype. And after that, we gain insight of a disease mechanism. So this is a workflow. The good thing is we are using the Broad Institute links data that tens of thousands of treatments applied to 20 cancer cell lines. A lot of people do that. But here, a lot of people are using the signature from the disease, from patients as a target, and do the computational procedure, try to reverse this disease signature. And after they generate the candidate, they validate it in a new system. Here, we are doing the prediction based on the target signature from cell culture, and we are doing the validation in the same cell culture. So I think this is one of our benefits that comparing to other people that are using the Broad Institute data. So this is an iterative procedure of heat predictions and in vitro validations. Again, same system between here and the original screening, and the mechanism study using computational methods. This is a design for the cell culture system. Again, it will automatically accumulate p-tau, phosphorylated tau, and we have a combined library, and we try to find which drug can effectively eliminate phosphorylated tau. So we identified two of the drug may be serving as a positive control, and then we use we review the results by eyes to identify some of the screening hits. This time we have a clear positive control. If the p-tau is gone, it's gone. It's a hit. So then we train a deep learning model. Because the data set is large, we want to carry out an automatic hit call. So we train a deep learning model based on the GoogleNet inception and use transfer learning and achieve good results in the training set and we applied it to cause heat versus non-heat with some validation, with human validation. So we obtained 38 primary heat, and this is the heat, the effect basically look like this. And we just obtained the transcription profile of 22 of these 38 heats, and to see that what they do in the gene pathway level. And this 22 primary heats, again, we are doing the same thing, try to stratify the heat group. They all have similar phenotype in the screening. So, but are they doing it through the same mechanism? Turns out they are not. Like this, we have 4 calcium channel blocker, and these 4 calcium channel blocker, when we try to cluster the transcription profile of them, 3 of them clustered together, but the other one clustered with a different group of hits, and this gave us some clue that where to look at when we do the prediction of better hits. So we have 33 of the 38 compound our collaborators do the biochemistry-based validation, and most of them can effectively reduce p-tau, and some of them can also reduce A-beta level. Which means that most of them doesn't touch A-beta, directly eliminate p-tau. And we want to generate more hits from existing hits. So we use a connection digest app. This is already retired. So right now we are using the Touchstone app in the Broad Institute platform. But this is how we did it. So using the 22 transcription profile from existing hits, we generated more than 6,000 candidates that showing the similarity of transcription profile with at least one screening hit. And we eliminated the one that already screened, and we take the 70 of them that are actually approved the drug, so that we can be closer to clinical practice. And we also take the 57 of them that are under clinical trial for others. So we have 470, and we go through the pharmacology filtering criteria, eliminate the toxic one. We look at whether it can be used systematically and whether it's commercially available. So we identified 27 approved drugs that may generate the same phenotype. So we successfully validated that 5 of the 27 predictions actually succeeded. This is more than 160-fold improvement than the blind screening. So, but it's still less than 30%. We want a higher successful rate. So we want to do from more to better hits. We go deeper into the links database. Links data actually treat each drug on 7 different cell lines in 6 different dosage. So we have a dose response curve in gene level, and we have the dose response curve in the phenotype level. We want to see whether we can have a matched dose response curve between phenotype and gene expression. And this is a result we do also based on the links data, but for the Parkinson's disease project. This drug nilotinib, and for the data on HeLa cell line, we see the significant dose response curve. And one of those genes, USP13, has been linked to the ubiquitin process related to Parkinson's disease gene called alpha-synuclein. So we found that two of the primary hits actually clustered very close. So we want to see that whether they have any shared gene changes. We found that they actually share a subnetwork, that both drugs will impact the immune-related subnetwork and centering the STAT1. And STAT1 is mediating the activation of microglia in the neuron microenvironment and activate microglia to increase the uptake, the A-beta in the process. And the question is whether this procedure goes through this known STAT1 regulator SOX1, because our data shows that. But there are no previous knowledge that microglia will have increased SOX1 expression level. So instead, in addition to the 27 approved drug, we also have 29 clinical trial compounds. We predicted these 29 compounds. We try them this time. They all works. We have a 100% successful rate, and two of them people are already linked, already used for AD study. One is this one. This is called ABT 737. One of the form, ABT 263, is a drug developed based on this. People are linking this to AD through the senolytic effect, meaning that this drug is proved selectively killing the cells carrying the tangled A-beta. And another one is this one. It's called PUAD. This one is in clinical trial phase 1, and so people are looking at the effects. So $1 million question is whether the other 27 we can find anything useful. So at the end, I want to say something that this is the greatest game of our time. This is Miracle on Ice, the 1980 Winter Olympic round-robin game for men's hockey between Team USA and USSR, Soviet Union. Soviet Union haven't lost a Winter Olympic game in 20 years. They are mighty. They are de facto professionals. And the USA, Team USA, they are just a bunch of college graduates, yet led by coach Herbert Brooks, and the heroic performance of all the teammates. So Team USA beat the USSR. But this game, the greatest game of all time, doesn't guarantee the gold medal for Team USA. You see, the final stage of the ice hockey in that Winter Olympic is a round robin, meaning that all the top teams have to play each other at least once. After Soviet Union game, the Team USA still have to play Finland. And because in Game 1, Team USA only managed to draw with Sweden, Team USA cannot lose this game. Otherwise, one loss will beat one loss and a tie. But after 2 periods of 20 minutes, Team USA is falling behind. Hence this question, we are going to win the greatest game of all time and lose to the Finns? Luckily, they found the purpose. They converge their power, and they work as a team, and ultimately capture the gold. They all converge on the podium designed to hold one people, to hold one person. This is a mini miracle by itself. What I want to say here is, I'm a bioinformatician, and during my career, I was asked multiple times, Zheng, we have a paper that's almost done, and we just need one picture, one more round of review, and we will do it. This is the greatest paper of all time. Sure. And for multiple times, luckily, for me at least 3 times, I was able to pull it off, and finish the final touch for the paper in the high-impact journals. As a bioinformatician, I'm honored if you invited me to your project at any stage, and I sincerely believe that you have done the greatest research of all time, and the question is, just let's put our power together and be the things. But of course, it will be more appreciated after those experiences. We can come back together to do more research projects, to start from the beginning and to go all the way. So let's do the conclusion. I think converge in the mathematical sense, it means quickly approaching a limit of numbers. Here in the network modeling, converge requests the existence of a focus. Like in that 3-layer network model, we use phosphorylation events as a focus. We can try other focus, right? And the second point is we need to carefully design the validation procedure for our discoveries. And we can apply new technology like deep learning to generate more advanced image features, and the single-cell sequencing, imaging set-off. Those will allow us to see the omics data in the same scale like the imaging data, in the single-cell level, and maybe from time-lapse. But the limitation is the coverage. You sacrifice the coverage of the imaging set-off if you do imaging set-off. Even the single-cell sequencing doesn't cover the complete genome. That means you have to go back to the unbiased method. And although the scale doesn't exactly match, you try to generate a useful hypothesis, and you open the door for more hypotheses, for more focused profiling methods like imaging set-off and single-cell sequencing. And we are actively working to converge image and transcriptomic data to improve the width and depth of drug repositioning in cancer and Alzheimer's. And we need cross-validations through all kinds of cell models, not only one model. That's the meaning of depth. We need a better understanding of the disease so that we can generate more versions of models, better models, to cross-validate of discoveries. And maybe we need a wider coverage of omics, not only transcriptomes, proteomics, maybe microbiome, things like that. We need to incorporate them. So this is a very, very long acknowledgement slide, and some of the persons that are very important to my Houston Methodist experience is actually here, like Miss Michelle Stelheff. She's actually the first Methodist employee we talked to. She's an expert of HR immigrant office. And we were still in Boston when they called me. She insisted that we can talk to him on the phone one by one so that she can make sure that we're okay. We belong. We will be accepted. And she backed it up with his word. With her words. During my 10 years before green card, I have 9 DS 2019 forms and 4 different versions of H1B paperwork, all handled by Michelle and her team. And the Houston Methodist Hospital Foundation, Miss Wilson, Miss Johnston, they have our group maintain relationship with the foundations, with the outside support, and gave us the support we need to carry out carry out our study. And Mr. James Mancuso is here. So after I published, after my Nature Cell Biology paper was accepted, April the 2nd, 2013, the first thing I do in the morning is go find Mr. Mancuso and talk about, the Astros break out the Yu Darvish perfect game. So that was a perfect game. Yu Darvish carried into the 28th batter, and the Astros, the lowly Astros, broke it. It shows that everything is possible. And I want to acknowledge the original 7. The original 7 members, bioinformatician, that come from Dr. Wang brings from Boston to Houston. All the other 6 people are already holding the professor level position all over the world. So, and also Dr. Zheng is here. If Michelle is the first Methodist employee we talk to, Dr. Zheng is actually the first Department of Radiology collaborator we ran into. Basically, me and Fuhai just literally ran into her and say, you look new here. And then we come from the Professor Wang's group. We're actually from the same group. And it all starts, so we have an original 7, we have a huge group to follow, and we have all those wonderful collaborators in Boston, Dr. Eugene Lai in the Department of Neurology, and Dr. Zhuba Wei is here, and all those excellent collaborations. So at last, please allow me to cite the great Vince Colley during his Hall of Famer induction. He told a story saying that once upon a time, there was an Indian tribe surrounded by the mountain, and the chief of the tribe want to test the manhood of the 4 warrior in his tribe. So he said that you 4 just go up, climb up the mountain, and go as high as you can, and take something to prove that you reach there. So early in the morning, the 4 braves just got on their way. And early in the afternoon, the first brave came back, and he brought a twig of spruce. And later in the afternoon, the second brave came back. They bring a ball of pine, and around the dinner time, the third one came back, and they brought some alpen scrap. So it was not until all the stars shine from the high heaven, the 4th brave come back, and all the people surround him with curiosity. How high did you climb? What did you get? The brave said, where I go, there are no spruce. There's no trees to shed me from the sunlight. There's no flower to cheer my path. There's only hard stone and barren land and snow. My feet are torn. I'm back home late. I'm empty-handed, and I'm all exhausted. But his eyes, a glamour light showed up in his eyes, and he continued, but I saw the sea. I came here 12 years ago as a PhD student still searching for my first paper. With the help from all of you, I got there. I saw the sea. When I continue my journey, I believe that I will not work alone. And for that, I thank you. I'm open to any questions, and would you please come over to the microphone in the front and so that we can hear and the recording can get all the questions.
Any question for Jim? Covers up quite a lot of material.
Good talk. So I would like to take this chance to ask Jim some of the academic question, basically. So when I talk to someone about their job repositioning skill, use a linked transcription data, they tell me they have some kind of concern. If we use a linked state to predict job, to use in neuroscience research, because the cell line, most of the cell line in linked state, they are tumor cell line. So tumor cell line, they have different transcriptome profile with human neural tissue, especially for the matrix neurons and agent brain tissue. So I just wonder, so what is your opinion if we use this kind of data to predict drug and then finally to use it to treat the neurodegenerative disease or some other neurological disease? So this is my first question. The second question is, I noticed you used, when you try to find some drug, use transcriptome data. You predict based on the similarity, transcriptome similarity, right? Actually, some of the drug, they may have many targets. They may have, so for example, if we get 20 drugs, each drug then have 20 or 30 targets. So how can you figure a way to overlap those targets and link the effect on the transcriptome profile to a specific phenotype? For example, in here for Alzheimer's disease, you say this drug may reduce tau phosphorylation, but actually those drugs, when you overlap the target, they may have some other target, not only target on the tau phosphorylation. So how can you figure a way to select this specific gene signature is related to tau phosphorylation, but not for other? Right? Also, actually this is a question relevant to my section 2. So based on this kind of technique issue, how can you figure a way, so when you select when you do drug prediction, use a transcriptome profile, how can you decide the minimal sample size? What is the suitable sample size? For example, if you need a 30 or 40 or 500 drug to predict your gene signature profile, then they may have some problem. For example, when we do some drug screening, the positive hit may be 1,002 or 1,003. When we screen 5,000 drugs, we only can get 5 of 15. So do you think this hit is enough for you to do this kind of gene signature-based drug prediction? Yeah, this is my question.
Thank you. So my answer is the data is data. Data is right there. Our solution is just to understand our own model better, especially the feature of the 3D cell model. Our collaborator is generating different versions of a 3D cell model, so that whatever predictions we made, we can validate them using multiple versions of the 3D cell models with a different composition of microenvironment and related to different communication mechanisms between neuron cell and other member cells in the microenvironment. Sure, such the success rate of such prediction can be low, but when we know better the meaning of our own model, and know better that how each drug can achieve the elimination of p-tau in our own model, maybe we can refine the target signature of the linked search. So I still claim that one of the benefits of methods comparing to other methods using links is that we are actually using the same cell models between the target signature and the validation models. The shortcomings of the transcription data will be there always. So we are working with the collaborators to generate better model of AD. So if we understand what this cell model do, and we can do the better prediction to see that we want to use this drug to like the same cell model do the same thing. Not directly take a patient signature, do the calculation using completely different group of cells, and validate using a third group of model. Here, the target signature and the validation, at least, we make sure they are from the same place.
Any other question for Zheng?
I don't know if I should congratulate you, but I will anyway for having great results in a hard system in cancer and then moving them onto an even much harder system.
Thank you.
But particularly with your model, where you're doing the high throughput or the high content imaging on the neurons, I think one of the first limitations that most people would start off is looking at is only takes into account one or two cell types. But your results, particularly in this stuff, where you find things that relate to neuroinflammation, kind of seem to have overcome that. And once again, you've made it a more difficult, take on something more difficult than was before. But my question here is, this seems to be a really important question right now. It seems that neurons are a target for the immune system, particularly T cells, but only in certain circumstances. So how do you find out which of the pathways that you find are actually relevant to the disease state? For instance, when you find almost everything up there results in T cell activation.
Yeah.
But how do you know in which cases say that the neurons express MHC so that they be targets of the T cells in the first place?
So I don't have the ability to zoom in on certain pathway, but luckily our collaborator, neurobiology collaborator, zoomed in on state 1. So they tried multiple procedure here, and they took the darkest node, which means the best p-values. And they find that this one, ST81, actually related to increased uptake of A-beta of the microglia after the treatment of these two drugs. So again, these are from the bulk microenvironment. So these are from the 3D culture consisting two types of cells, neuron and astrocyte. And one thing we are doing is to do single cell sequencing to attribute the pathway activities to specific cell types, and to build a more detailed crosstalk model and correlate them further to more detailed phenotype. Not only the elimination of p-tau, but T cell activity, the uptake of a certain protein, things like that. And luckily, we have the collaborators. Based on this very rough results, they generate the hypothesis. They have a more focused method. That's what I talk about, that such a convergence of unbiased large-scale profile actually open the door for hypothesis generation and allow us to use more focused methods to do deeper study.
Go ahead.
Actually, let's talk first the congratulations. I'm top. Actually, congratulations to you. Nice talk and
Thank you.
research. And I learned something about the bioinformatics, how to do that from you. And I really think about the targeting the cell morphology. That I think that's a good idea for the new strategy for the therapy. That's a good idea. One quick question about that is you use the several tumor cell lines, right, from different tumor types.
Yes.
But did you get some similar phenomenon from patient samples? Yeah, patient samples, cancer patients.
Yes. So,
what concern is that because the cell line, if a culture in vitro, that's for a long time,
yeah.
it will change the morphology, in vitro. So I'm just wondering.
Yes. So basically, this paper started with 18 breast cancer cell lines. The end result is that they use all those shape-correlated genes and mapped to a database of breast cancer, the medical imaging for breast cancer patients. And at the end of the day, they link some of the shape feature and shape-correlated genes to the prognostic of breast cancer patient. They actually identify the feature like nuclear eccentricity, things like that, from the H&E tissue, from the medical imaging. Those type of features can actually serve as a very good predictor for patients' prognostic features. So yes, we indeed saw the correlation between the cell line data and the actual patient data, and we are actually actively using those patient image data to validate our results. By the way, that's Dr. Yang from MD Anderson, and Dr. Yang having published, included me in her publication in Science Signaling, and this gave me closure with this journal, because our Nature Cell Biology paper actually rejected by Cell Science Signaling on the day my son was born. So they saw the email, the collaborator from London go, do you have time for a talk? You'd better be hurry, otherwise they will start pushing any time. And he called me from London. So we talked about it. And another thing is, that's the day my son was born. And when the paper was finally accepted, my son was ready to go to the kindergarten. That's how far I have to go. But hopefully, I'm lucky to surround myself with so many excellent collaborators that reach the biological and medical knowledge, and I cannot do everything, and I just focus on my thing, and hopefully I can give you some indication and hypothesis, some spark because data is data. Data is right there. We just need some way to get it out, to just get the mouse out of the piece of wood, like a novel said. And I think I will rely on the biologist and the doctor to lead me deeper into the biomedical study.